Hey guys, today we're going to be talking about trigonometry. So we're going to be doing a little bit of an overview of the grade 10 stuff, a little bit of review, and then talking about how to use new trig laws to solve triangles. So these include the sine law and the cos law, and also the ambiguous case for the cos law, which is honestly the most annoying part of trig 11 in my opinion. We're also going to be going over the inverse functions of trig and how to use that to solve for degrees theta. Let's get started. So trig is composed of three primary functions, being sine theta, cos theta, and tan theta. These functions are a little bit special in that they don't take an x-coordinate, what they take is a degree. So you feed the function a degree, you can actually think of this as just f of theta. And what this function does, is it constructs a triangle with this degree, and then it spits out a ratio comparing one side to another. So how much bigger one side is than another. In the case of sine, this is the opposite and the hypotenuse. In the case of cos, adjacent and hypotenuse. And tan, opposite over adjacent. So what do I mean by this? Let's just say we had sine theta, where this angle right here, that's theta. I'm just going to remove this for clarity. Well, what sine is going to do is it's going to take the length of the opposite. I'm going to label it x, and it's going to take the length of the hypotenuse. I'm going to call that x2. And what it does is it compares them. So it takes x and divides it by x2 to yield a constant. This constant represents the magnitude of the sides compared to each other. So if sine theta is equal to 0.5, that means that x is half of x2. That's because when x is divided by x2, it yields 0.5. So that means it's basically just 1 over 2. So that's how we can say x is half the size of x2. Say we had a cos function now. I'm just going to erase this out. So we had a cos function. We feed it theta, and it constructs a triangle using theta. Now cos compares adjacent to hypotenuse. So it's going to take the adjacent side, this side, and it's going to take the hypotenuse side, and it's going to divide them. So let's just say, again, cos theta is 1/2, or 0.5. Then, even though it's not visually accurate, like, you can ignore the diagram. I'm just trying to illustrate which sides are being compared. If cos theta is 0.5, then that means we know that the adjacent side is 0.5 times the hypotenuse. Or in other words, the hypotenuse is 2 times longer than the adjacent is half the size of the hypotenuse. And that's what these trig functions do. Tan does the same thing with the opposite and adjacent side, which is this side and, again, the adjacent side. But to save time, I am not going to get into that. Now, what you can do with these ratios is you can actually take a length. Let's just say we know our hypotenuse length. It has a length of 3. And we know that our theta is 30 degrees. If we know that sine theta is equal to the opposite over the hypotenuse, but we know theta and we know the hypotenuse, why don't we just multiply both sides by the hypotenuse, so we get h sine theta is equal to the opposite. So what I've done here is I've multiplied by h, and then plug in the values. So we get 3 sine of 30 is equal to the opposite. That is how you use a sine ratio to yield a side. You can actually also do this with missing adjacent side with cos value. but I am going to fully compute the example given first. Using a calculator, I could determine that sine 30 is 0.5. So our equation ends up being 3 times 0.5 equals the opposite. So the opposite side must be 1.5. And then we can use Pythagoras' theorem to solve the rest of the triangle. Now let's try this with cos. Given cos theta equals a over h, and a triangle that looks just like the last one, but this time we have the adjacent side which is 2. How can we solve for the hypotenuse? Well, we will want to isolate the hypotenuse because we have the degree, which is 30 degrees, and we have the adjacent. So we've got 2 variables missing 1. Then it's just a simple method of multiplying both sides by h. So we get h cos theta equals a. But we know cos theta, we don't know h, but we do know a. How do we isolate h? We can divide both sides by cos theta. So we have h equals a over cos theta. Now, let's plug the numbers into our calculator and permutate it. H is equal to 2 over cos 30. Now, what is cos 30? Well, pull out your calculator and type in cos 30. So now we get h is equal to 2 over 0.866. Simplifying the fraction, we get 2.309. And that's our hypotenuse. Notice how we solve this using trigonometry when otherwise it would have been completely unsolvable with the Pythagorean equation. That is the power of trigonometry. Okay, let's move on. Now let's talk about some inverse functions of trigonometry. So sine theta is a function where you plug in a degree and it gives you a ratio. There exists a inverse function called arcsine theta. It's commonly written as sine to the -1 theta, but you also see it literally being wrote as arcsine theta. This function is an inverse function to sine. So recall that if a function is applied to its inverse, it spits out the original input. So basically like cancels out the function. The trig function inverse functions work the same way, where sine of arcsine theta just spits out theta. Now, since the arcsine is the inverse of sine, and sine takes in a degree, spits out a ratio, arcsine must therefore take in a ratio and spit out a degree. So we plug numbers, pure, like raw, normal numbers, into arcsine, and it'll spit out the degree for which the triangle given has the ratio. So let's take a look. Sine theta has arcsine theta. Cos theta has arc cos theta, or cos -1 theta. And tan theta has arctan, or in this case, tan -1 theta. All of these functions, when applied to their inverse functions, will just yield the original degree. Similarly, arcsine of sine also yields a degree. Same thing works for tan, cos, all of the others. You can use these to nullify trig functions. And so how would we use this in a practical setting? Well, it would have to be for when we have two sides but no degrees in a triangle. Let's take a look at this triangle right here. We have the opposite side with a length of 1, and we have the hypotenuse with a length of 2. What's theta? Well, we know that the inverse trig functions will take a ratio and they spit out a degree. That's exactly what we're looking for, isn't it? So we use the arcsine function. Sine -1 of the sine ratio, which is the opposite over the hypotenuse, so of 1 over 2, is equal to the degree. This actually makes sense, because what you're actually doing is you're doing arcsine of sine theta. Since sine theta is the ratio of the opposite over the hypotenuse, in this case 1 over 2, we can basically just do a 1-for-1 swap. So we swapped sine theta for the ratio, since they're equal. And then what we've got now is a nullified function. So, plugging this into a calculator, we get, hold on, Marcus, cut this out in post. We get arcsine of 1/2 is equal to 30 degrees. Let's try another one. No, hold on. Let's say we're given a triangle with now it's going to be an adjacent. The adjacent is going to be 2, hypotenuse is going to be 4. Since we have the adjacent and we have the hypotenuse, the trig function that involves both of these is cos theta. And that tells us that we can use the inverse. So arc cos, and feed it a ratio, the ratio of the adjacent to the hypotenuse. Given that the adjacent is 2 and the hypotenuse is 4, we feed it this ratio right here, 2 over 4, which is the same thing as 1 over 2. So I'm just going to write it as 1 over 2. And that should spit out our angle theta. Again, this works because adjacent over hypotenuse is equal to cos theta. And what we are doing is we are taking this ratio and we are swapping it 1-for-1 in the nullified function. So we basically just did arc cos of cos theta. And we all know that's going to yield theta. So once we plug this in, it will just spit out degrees. So in this case, plugging it into a calculator, we yield 60 degrees, or no, actually, we don't need to get into radians yet. All right, now that we've familiarized ourselves with solving for degrees and triangles, and I highly recommend practicing more practice problems for these, we need to address some special rules. So the sine ratio, where sine theta is opposite over hypotenuse, this only works for right angle triangles. If we want to get into scalene and isosceles triangles, we need to use some special rules to start figuring out these angles. But before we get into this, let's get into some labeling conventions for triangles, because it just makes everything a lot easier to understand, and also will help with university and higher level maths as you go into it, because these questions do tend to use triangles ABC instead of actually giving you a photo. So generally a triangle will have 3 angles, and these are labeled with capital letters. These can be anything from A to Z. Common ones are triangle ABC, triangle JKMN, and just like sets of letters that are really close together. So, triangle ABC, which we will be doing for now, is as follows. You have angle A, opposite side lowercase a. Angle B, opposite side lowercase b. And angle C, opposite side lowercase c. Usually you would actually have your A angle like this, but it really doesn't matter what the sides are labeled as, because, you know, it's just whatever you want to call it. With this in mind, let us construct a scalene triangle. Something like this, maybe. We're going to construct a scalene triangle ABC, and we're going to use it to demonstrate the two laws that we will now cover. So I'm going to erase everything up here. See how I label degree A, degree B, degree C, and A is opposite A, B is opposite B, C is opposite C. Lowercase is sides, uppercase is degrees. Now, the two rules are called sine law and cos law. We will cover sine law right now. Sine law is as follows. Sine of A divided by A is equal to the sine of B divided by B is equal to the sine of C divided by C. Now, sine law can be applied when you have a sine angle opposite pair. So let's say you have A and you have A, and you have anything else in the triangle, whether it be uppercase or lowercase, you know, side or degree. All you need is something else. So I'm just going to give us B. Let's just say we have side length B. And let's put some numbers to this. So we have sine A over A. Let A be 20 degrees. And side length A be 2. Let B, let's say it's 4. Now what we can do is we can feed sine of 20 degrees over 2 into our equation. And that is going to be equal to the sine of B over 4, because B is of length 4 and A is of length 2. Now, pull out your graphing calculators or regular scientific calculators, anything that can permutate trig, because you're going to need them for this unit. To solve for B, what we're going to do is we're going to use our graphing calculators and our knowledge of trigonometric functions to isolate B and then plug them into a calculator and solve for it. So to kick things off, we have sine 20 over 2 is equal to sine B over 4. To isolate sine B, first we're going to get rid of the 4. So we're going to multiply both sides by 4 to make sine 4 over 2, sine 20 is equal to sine B. That just equals 2 sine 20 is equal to sine B. Now, remember what we talked about before. If we take the arcsine of a function, it just leaves us with the degree. It takes a ratio, it spits out a degree. So what we can do is we can take the arcsine of both sides. So we get arcsine of 2 sine 20 is equal to the arcsine of sine B. And since these functions are inverses, they cancel out, leaving B. Plugging this into our calculator, we get B is equal to 43.16 degrees. Now, notice I've erased my triangle. That's because before, the triangle was drawn inaccurately. And sometimes with trig problems, this will happen, because you're not sure of what shape this triangle would take until you figured out a second angle. So in this case, if the first angle was 20 degrees, and this is angle A. Second angle is 40-something degrees. Then the triangle would look it's curving inwards. So B is 43.16 degrees. Now, what we need to do is we need to solve for C. But we know for a fact that all triangles have a total of 180 degrees between all three angles. And since we know two of the angles, we can just subtract them from 180 to solve for the third. So solving for C, we get 180 degrees minus 43.16 degrees minus 20 degrees. That gives us 116.84 degrees as C. Now, since we actually already have the lengths of B and A, what we can then do is we can use sine law to figure out the length of side C this time. So, just like before, we have sine 20 over 2 is equal to sine C over C. We know that C is 116.84 degrees, right? Yeah, 116.84. And now all we need to do is rearrange this equation to solve for C. So we're going to multiply both sides by C. So we get C sine 20 over 2 equals sine 116.84. This just raises up the C from the denominator and allows us to isolate it by doing further operations. So next we're going to multiply both sides by 2 and then divide them by sine 20. I'm going to do this all in one step. So C is equal to 2 sine 116.84 divided by sine 20. Plugging this into our calculator. We get C is equal to 5.2176. And this actually makes sense because the hypotenuse is always going to be the longest side and the second longest side is only 4. So sometimes you're going to get like an outlandish number, like a negative number. Chances are, if you get something negative, you've made a mistake. The hypotenuse should always be the biggest side, and it shouldn't be that much bigger than any of the other two sides in the triangle. All right, let's start with using Koh's law to solve for a side-side-side case. So this is a case where you're given three sides of a triangle. So let's say we have A equals 5, B equals 7, and C equals 10. So the first step would be to solve for the largest angle. This gives the triangle an anchor and allows you to solve for the rest of the triangle based on that largest side. So the largest angle will always appear between the two smaller sides. So in this case, length 5 and length 7. I will draw it out now. Length 5, length 7, length 10. As you can see, the largest angle appears between the two smaller sides because the largest side stretches these angles outwards. Now, since we have the lengths of all these, I'm just going to label this A side, this is B side, C side. We are going to want to try and solve one of these angles. So I've picked this one at random, angle B. Now we can use Koh's law to solve for cos B. So we will use this variation. B squared equals C squared plus A squared minus 2CA times cos B. Before we solve for cos B, we first need to rearrange the equation so that we can just get cos B on its own. We can do that by moving all of the loose terms over to the side. So B squared minus C squared minus A squared equals negative 2AC cos B. I'm going to delete the triangle just so that we have a little bit of space. I'll redraw a smaller one down here. Now we can divide both sides by negative 2ac. So we have b squared minus c squared minus a squared over negative 2ac equals cos b. Take the arc cos of both sides to isolate b. We get cos negative 1, b squared minus c squared minus a squared over negative 2ac equals b. And then now all we need to do is just plug into our values and then plug it into a calculator. Let's do that now. All right, plugging this into our calculator, we get, first of all, let's do the numerator inside the function. 7 squared minus 10 squared minus 5 squared is equal to negative 76. Our denominator is equal to negative 2 times 5 times 10. So our denominator is equal to negative 100. So now let's take the arc cos of 0.76, because that's what this evaluates out to be. Plugging this into our calculator, it spits out 40.5 degrees, which is just b. So now that before we move on, we need to talk about a special situation in trigonometry, and it's called the ambiguous case. So this happens when we try to solve for an SAS triangle using the law of sines, but the information that we are given leaves more than one possible answer. So this only happens under a specific condition. It happens when we know two sides and one angle, where the angle is opposite the side. So it happens when we know A and B, and either A or B, where A or B are angles. Big A, big B are angles. Now let's imagine that we're given an acute angle and two sides. When we try to solve the triangle, we might find that 1, no triangle is possible. 2, only one triangle can be made. Or 3, 2 different triangles can be formed. So let's look at each case. Number 1, we are given A, length A, and length B. Now, if to say, since we have angle A, we have a predetermined height, and we have a predetermined hypotenuse. If A were to be shorter than the height, sorry, I mislabeled this. This is the height. If A were to be shorter, say it was something that looked like this, we actually can't form a triangle because we already know the angle A, so that basically locks these two arms in place. We can't move them. We can't try to compensate for the lack of length of the opposite side. So if our angle looks like this, where A is shorter than H, no triangle. Another case is when A is equal to H. If your opposite side is exactly equal to your height, that basically just forms a right-angled triangle. This is the only possible solution because the heights and the other side change with each other perfectly. They are the exact same thing, and there is no ambiguity whatsoever. It has to be a right-angled triangle if H is equal to A. Now the third case, or the ambiguous case, is where you have two different triangles that can be formed. So let's just say we're given a triangle. We know that angle A is opposite side A. I'm not going to draw in side A yet, you'll see in a second. And we know that we have a length B. We also have a height h. And we know that A is greater than h. What that means is, if we were actually to draw a straight line being A, it's a lot taller than h, so it has to bend to be able to create a triangle. And given that we don't actually know the length of C on the bottom, what this tells us is that we don't know whether this triangle will be created or this triangle will be created. Both are equally possible because A is bigger than H, so it could swing both ways, and we don't know C. Angles A and angle C, well, sorry, only angle A stays the same in this case, but we don't know C. We also don't know this bottom angle right here, angle B. We don't know that. So since we don't know these, both of these triangles are possible. Now, I'm going to plug some values into here, and let's just try an example. Let's say we're given the following angle of angle A is equal to 40 degrees. Side A, 7 centimeters. And side B, 10 centimeters. What we can do is we can try and use the law of sines to find angle B. The law of sines tells us that sine 40 over 7, which is angle A over A, is equal to sine B over 10, which is sine B over B. Rearranging for B, we get 10 over 7 times sine 40 is equal to sine B. Taking the arcsine of both sides, we get B is equal to, and I'm just going to punch this into my calculator here to save time. .67 degrees. Since this is an ambiguous case, however, we know that there is actually another possible angle for B. If we were, since sine is positive in both the first and second quadrant, if we were to take this as the first case, and since we've flipped it around the x-axis, these two angles are the same. So this would be this and this. They're the same angle. I'm just going to label them 66.67 degrees. We now must find this angle. And to do that, since the angles on a straight line equal 180 degrees, we can simply subtract the interior angle that we've already solved for, 66.67 degrees, from 180. And then we're left with, what is this, 113.33? No, 33. 113.33 degrees. Now that we've constructed our two different possible triangles, we must solve for both cases of angle C. So C1 with this triangle, and C2 with this triangle. Since angle A is the same, I'm just going to continue down here. C1 is equal to 180 degrees minus angle A, which is 40, minus our first case, so 66.67 degrees. That would give us, and I'm just going to punch it into my calculator, 73.33 degrees. C2 will give us 180 degrees minus, again, our angle A is fixed. But our angle C is not, and C is determined by which of the ambiguous cases we're doing. So we've used the first value of C, now we're going to use the second one. So now we're going to subtract 113.33 degrees. And we get 26.67 degrees. So our two triangles in the end would look something like this. And I've only solved for the angles here. You would need to use sine law to solve for the sides, but just for the sake of time, I will do it angles only. C1 has three angles. These angles are 40 degrees, 66.67 degrees, and 73.33 degrees. C2, since we're given A, we know that this is a constant. 40 degrees, 113 degrees, and 26.67 degrees. And boom, there are the two ambiguous triangle cases.